Welcome to the fourth lecture of EE311. In this lecture, we will continue on the analysis of the common source amplifier. Previously, we have shown that for a common source amplifier, we can use superposition to analyze the circuit in DC first and then in AC. And we started with the DC analysis and most basics in the previous lecture. So let's refresh our memories from the previous lecture very briefly. So we said that we are working on a common source amplifier. Let's remember the structure very briefly. Sorry, this should be a current source. I and C2, let's say this is C1. And RL V out. C3, let's say VDD. This is source. This is VS. And when you are dealing with this structure, we name it as common source because source is AC-wise grounded. So the name comes from this source AC-wise grounded. So this is common source. And keep in mind that as a designer, you have a control on this part only. You don't have a control on the source and you don't have a control on the load. So RL and RS or VS is set by the customer or the end user. So as a designer, you can control these resistances or the transistor parameters or the biasing parameters. So this helps to understand some of the principles in the later explanations. So let's say this is RD. So what we do is the first step is DC analysis. And why do we do DC analysis? Two reasons. First, we have to show that the transistor operates in the proper region. What does this mean for MOSFET? It should be in saturation. And how do you show it? You have to check the conditions VGS larger than VTN, VDS larger than VGS minus VTN when ID is equal to the saturation current, which is 1/2 Kn VGS minus VTN square. And keep in mind that we don't consider this channel length modulation for DC analysis. So this part is related with channel length modulation. And you don't need to worry about it for DC analysis. So ignore for DC analysis, okay? So this is the first purpose of DC analysis. And the second purpose is, of course, finding small signal parameters, which we haven't done yet. And in this lecture, we will deal with this as well. And then the second step is, of course, small signal or AC analysis. But please be careful when you are using this term small signal and AC. They are not the same. You know, the small signal inputs are AC, of course, but not all the AC signals are small signals. So we have to make the difference between them or the definition for them separately, and we will consider it in the coming lectures as well. So right at this point, we did up to this part. Now we are going to work on this thing. But before continuing, I want to solve one DC biasing problem to clarify it in a better way. So let's solve an example on DC biasing. assume that we have a circuit given by this schematic. VDD, let's say RD, which is equal to 620 ohm. RG given by 1 mega ohm. RS 200 ohms. We have some C2 capacitance, and then C3 RL V out, and at the input we have another C1 capacitance, some voltage source Vs, and we have a different drawing in here which indicates that MOSFET is depletion type NMOS. So what will be the difference by using a depletion type NMOS? Basically nothing. All the DC analysis will be the same, but the only difference is the threshold voltage is negative. That's the only difference. Other than that, we are going to use the same mathematical formulas and everything. And in the this experiment example, they provide the parameters as Kn 10 milliamps per volt square, Vtn minus 2 volts, which is consistent with the type of the NMOS transistor, and lambda is given 0.02 volt to the power minus 1. And the question is, what is the quiescent point? In other words, they ask about ID VDS of the transistor. Okay, how you are going to approach this problem? Of course, first of all, I need to find a DC equivalent circuit. Assuming that C1, C2, C3 are large enough in DC operation, they are going to be open circuit. I don't need to worry about them. So the DC equivalent circuit will be reduced to this one, and you can redraw the DC equivalent circuit. It will be let's say the supply voltage is 15 volts VDD. This is RS. RG 1 mega ohm. So what you need to do is you need to start with an assumption. I make a mistake? No, I guess it's true. Okay. So we have to start with an assumption. Since the gate potential is at 0 volts, remember that the gate current of a MOSFET is 0. This gate voltage is 0 volts. And the threshold voltage is negative, which means that VGS is definitely larger than the threshold voltage. So this MOSFET should be on. If it is on, if it is conducting, if some current is passing through the drain, we have two choices. This transistor will be either in saturation or linear. And without solving it, you never know it. So at the beginning, we have to start with an assumption. So start with an assumption. And keep in mind that since we want to make amplifiers, we want this transistor to be in saturation. So assuming saturation initially can be a wise choice. So assume, let's say the transistor M is in sat. So what does this assumption mean? This assumption says that right at this point, ID is equal to 1/2 Kn VGS minus VTN square. And in this expression, Kn is known, it's given as 10 milliamp per volt square. VGS is unknown, ID is unknown. VTN is known as minus 2 volts. And please, notice that the type of the transistor is depletion, and I didn't change anything in the expressions because you use the same expression for depletion or enhancement type. It's not going to make any difference. The only difference is VTN is negative. That's it. It's not like the PMOS case. So I need one more expression in here. The other expression can be the equation on this line, which means that VDD is equal to potential drop across RD plus VDS, or sorry, yeah, you can write it like this. You can write another expression in here, which means that VGS plus ID RS is equal to 0. Again, in this expression, we have two unknowns. This is unknown, this is known, this is unknown. So by using two equations with two unknowns, you should be able to find VGS and ID. Okay, so let's continue. If you write the expression, then IDS will be equal to 1/2 10 milliamp per volt square times VGS minus VTN, which is plus 2 square, and also VGS plus IDS or ID, whatever you call, times RS should be equal to 0. So if you put VGS in this expression, you will find it as 200 IDS is equal to 4 times 10 to the power 4 IDS plus 4 minus 800 IDS. Also, sorry, I have to make a correction in here. So let's forget about this thing. ID will be equal to 5 times 10 to the power minus 3 minus 200 IDS plus 2 square. So from here you will have a polynomial, second order polynomial, and you have two solutions. One of them is IDS is equal to 0.02 amperes. The other one is IDS is equal to 5 milliamps. Which one am I going to choose? I have to check the conditions. I mean, if you use this expression, for example, VGS will be equal to minus 4, which is less than VTN. So conflicts with the transistor condition. So this cannot be a solution. But for the other one, VGS will be equal to minus 1, which is definitely larger than VTN, therefore it's okay. So you are going to choose this one, but not this one. And therefore, you get like IDS 5 milliamps. And VGS is equal to minus 1 volts. Now I need to find VDS. But from the schematic, you can write it as VDD minus IDS times RD plus RS. And in that case, you will find VDS as 10.9 volts, which is definitely larger than VGS minus VTN, which is 1 volt. So SAT assumption is verified. In this lecture, we will do it a lot. We will assume something, and at the end, we have to prove that that assumption is correct. That's the thing. I mean, you cannot leave any assumption open at any time. If you assume something at the end of the solution, you have to show that your assumption is correct. So this expression tells me that my SAT assumption is verified and my quiescent point VDS ID will be equal to 10.9 and 5 milliamps with SAT operation. If, for example, at the end of the solution, this condition is not satisfied, then my SAT assumption is wrong. I have to go back. I have to assume that the transistor in linear region. I have to use linear current expression and solve it accordingly. And then most probably the solution will show that the linear assumption was correct. So each time you start with an assumption and at the end you have to prove that your assumption is correct. So now we know how to deal with this DC analysis or DC biasing. We are moving on this path. We start with DC analysis. Now we need to find the small signal parameters from the DC analysis. Now what we can do small signal analysis. Let's name it as small signal. In small signal analysis, what you need to do is we are going to kill the DC sources. Killing means that voltage sources will be shorted and current sources will become open. Now we are going to short the isolation and bypass capacitors. Why? Because at mid-band frequencies, the impedance of the capacitance is 1 over j omega c. And keep in mind that we are always using large enough capacitors as isolation or bypass capacitors. Therefore, this multiplication becomes a significant term, and this thing will go to 0. Now, your small signal or AC sources are connected to the system. They are gonna be ready for the amplification, and we should replace the transistor with its small signal model. So let's remember what is the small signal model. So let's clear up this thing and let's start from the beginning. For an NMOS transistor, this is the equivalent model. So for an NMOS transistor, we have drain, gate, and source. So in small signal model, you replace it with this term. But you have to be careful about like this connection. Gate should be gate, drain should be drain, source should be source. And you replace the transistor with this equivalent circuit. And this hybrid pi model is the same for enhancement type NMOS, depletion type NMOS, and for PMOS as well. Even if you have a PMOS transistor, so this was NMOS, assume that now we are using PMOS, you are going to use the same circuit without changing any current direction or without changing any polarity in this hybrid pi model. But as I said, you have to be careful about the node connections. Now, source is this one, drain is this one, gate is this one. All of them can be simplified with this hybrid pi model. And I want to warn you about one more thing, the notation. In DC, we use capital letters generally. In AC, we use like letters like this one. So if we see something like this, VGS, this is AC. If you see something like this, this is DC. Okay. If you see a potential like this, for example, then this will be DC plus AC. So small letters, small subscripts are always for AC. Capital ones are for DC. If it is combined like this, it means that we are mentioning about both of them. So this drawing is also consistent with that. Like in DC analysis, you use large letters. In AC analysis, we are using like small letters. So this is the model. And in this model, there are two unknowns. One of them is R0, the other one is GM. And most probably you learned them in 212. And they have some expressions. I can write those expressions right away, but I don't want you to memorize it. Even if you cannot remember them, you should be able to drive it. So you should start with the definition. So R0 is the output resistance. So this is the output resistance. What is the definition of an output resistance? So it's defined as, of course, it's some voltage divided by some current, right? So it's like any voltage or one voltage divided by some current. So which voltage and which current? It's appearing at the output. Output is appearing between drain and source. So it is VDS voltage divided by ID current. But wait a minute, this is not a linear system. The VDS and ID dependence changes in saturation, for example. You can write ID with some expression of VDS. So it should be the partial derivative of it, like del VDS by del ID. We don't know del VDS by del ID, but I know the ID expression. So I can write it as 1 over del ID by del VDS. Let's remember the ID expression in saturation. I am using the saturation expression because this hybrid pi model can be used only if the transistor is in saturation, right? So it's the first thing. We have shown that the transistor is in saturation. That's why I have to use the saturation current expression. So this is the expression that we were using before. And as you see, it doesn't depend on del VDS, which means that this derivative is like 0. And therefore, R0 goes to infinity. But we ignore something in here, right? Which is channel length modulation. If you put channel length modulation back in this expression, 1 plus lambda VDS, now the derivation is quite easy. When you get the derivative, you will find it as del ID by del VDS as lambda times 1/2 Kn VGS minus VTN square, right? So this is approximately equal to ID. So I can say that this will be equal to 1 over lambda ID. I'm saying it's approximately equal to ID because, again, in the second part, in this part, the channel length modulation is ignored in the second part. So this is like an approximation 1 over lambda ID. So you can start with the definition and you can drive this output expression. There's another way to find it. Remember our famous curve. So this was our famous curve. So this x-axis is cutoff, and there is some border in here, VDS equal to VGS minus VTN. So this part was named as linear, this part is named as saturation, and the slope in here is because of channel length modulation. So we did this in the previous lecture, and we also said that all these lines are in fact like crossing at a certain point somewhere in here. even though my drawing is not clear to show it. And this point is like minus 1 over lambda, as you may remember. And again, you can continue with the definition. R0 is the variation of output voltage, VDS, with respect to input current. So if you take a look at much more closely in here, so R0 is in fact the slope in here, or 1 over the slope in here. So if you know the operation point or bias point, let's say that your transistor is operating at VDSQ and giving you some IDQ value, and the previous stage we make DC analysis and we find this thing. That's why we find it. Now we know VDSQ and IDQ, and therefore now you should be able to find the slope in here. And the slope in here can be found from this triangle. Okay, there's a triangle in here. I'm trying to find the slope, and that slope is in fact this thing divided by this distance. So I can write R0 as from that slope. R0 as VDSQ plus 1 over lambda divided by IDQ. And this result is a bit different than this derivation. But this was an approximation. In fact, you can approximate the second result like the first one. Why? Because in general, this 1 over lambda is a very large value. So this is in the range of like 100, 200, whatever. And any potential in a circuit is limited by the supply voltage. If you are using, let's say, 1.2 volt supply, the VDS voltage of a transistor cannot be larger than that supply value. It's not possible. Or if you are using a supply voltage of 5 volts, for example, any VDS voltage of a transistor cannot be larger than that supply voltage unless you are using some like extraordinary circuits. But which means that this term in here is much smaller compared to 1 over lambda. So this can be ignorable, and therefore R0 can be approximated as 1 over lambda IDQ. Now we know this output resistance. We don't have any problem with this output resistance. The second part is finding this GM. Okay. So let's solve that GM. Now GM is unknown, so let's try to find GM. Again, we can continue with the definition. GM is transconductance. This is the transconductance of the transistor. If it is transconductance, as the name implies, it should relate output current with the input voltage. So it is I divided by V. I is the output current, which is ID. V is the input voltage, which is VGS. Again, you have to use partial derivative in here. Now it is a bit more easier because it's going to be del divided by del VGS times Kn divided by 2 VGS minus VTN square. I am using the saturation current expression. Why? Because to be able to deal with a small signal model, your MOSFET transistor should be in saturation. That's why I'm using saturation current expression. And therefore, GM can be found as 2Kn ID or Kn VGS minus VTN. Both expressions are the same. They are just given by different terms, but you can check that they are the same. So GM can be given by any of this expression. Now I know GM and R0, and my hybrid pi model is ready to be used for AC or small signal analysis. Let's continue again. We learn hybrid pi, but there is another model called T model, which can be in some applications can be quite useful. It is given by this schematic, but I'm going to show you the derivation of T model from the hybrid pi model. So let's draw hybrid pi model first. This is gate. Always name the nodes. Do not forget it. It's a good habit to use the node names. This may save you from some potential mistakes. R0, GM, VGS, VGS, and drain. And in this model, of course, maybe it is redundant, but it's clear that the gate current is equal to 0. Okay. And also, I'm going to do one more redundant addition in here. I think I can add another current source in here with the same value of this current source. So it's not going to provide any extra information, but the advantage is I can drive the T model. This second term is definitely redundant. It makes the circuit more complicated, but it doesn't change anything mathematically. Up to now, I didn't change anything mathematically, although I add two redundant components in here. And why this current source is redundant? It is something like adding two current sources next to each other. Something like this. It is not meaningful, right? You can show it like this. 2A, that's the same. But it's gonna help me. So in this condition, by keeping this IG is equal to 0 term in here, may I connect this node to here? So let's think about it. Again, it shouldn't change anything mathematically as long as I put this condition in here. If I don't put this condition, I'm in trouble, of course, because I'm going to violate KCL and KVL. The second circuit will be definitely different than the first one. But as long as I keep this IG is equal to 0 in here condition there, I should be able to connect this node to this node without any problem. Okay, so my hybrid pi model is a bit changed. There are some two redundant terms in here. I made a connection, but mathematically, this is exactly the same with the previous one. So I'm going to go one step further. When you take a look at this potential, we have VGS. And look at the current source passing through here. It has a magnitude of GM VGS. So I can replace this current source with 1 over GM impedance or resistance. And this is not going to change anything mathematically again. Let me show it very quickly. So I'm going to put, again, gate is here. I'm going to add 1 over GM resistance in here. This is my source. There is R0. Here I have GM VGS. And this is drain. This is VGS. And do not forget to put IG is equal to 0 term in here. If you forget it, these two circuits will not be the same. Okay, that's the most critical part. So when you take a look at this circuit, the current passing through here is GM VGS. You can show it like it's VGS divided by 1 over GM VGS. That's the same thing in here, nothing changed. So these two circuits are equivalent to each other. And I can go one step further, just do some relocating these components without changing any parameter in here. So this is the T model. This is exactly the same with hybrid pi model. So hybrid pi and T model gives the same result for all circuits. You can use any of them. But why do we need to learn both of them? Because in some applications, T model is much more easier for the solution. You can see the solution very quickly. But when you are using the T model, there is one thing that you should be very, very careful, which is Ig is equal to 0. If you forget it, then it's going to change everything. It's going to change all the results. Anyway, at this point, we know the small signal model, and let's go back to our common source amplifier. What I was supposed to do for AC analysis, you can see it from the previous slides, which is kill DC sources, short isolation, and bypass caps, and replace transistor M with small signal model. So let's do it in here. I'm gonna draw the actual circuit in here for the sake of simplicity so that you can see it. The actual circuit was something like this. I'm gonna erase it later on. So this was the initial circuit. Or I can use ground in here. They will be the same. Some bias current, R1, R2, RD, RL, RS, VS. So start from the left. VS is an AC source. I'm gonna keep it as the same. So we have some VS signal, some source resistance. This capacitor will be shorted. So it's going to continue like this. And when you reach this point, you see two resistors, R1 and R2. R2 will appear directly because this is already grounded. But for the upper one, there's a DC source, and I'm killing DC sources. Killing means short voltage supplies, open current supplies. If I short it, this node will be ground in AC. Therefore, I'm going to put R1 and R2 as this. Why? Because I killed DC sources. The supply is killed. Now I reach the gate of the transistor. So this is gate point. At the gate, I'm going to replace the transistor with the small signal model. Let's use hybrid pi, but you can use T model as well. The result will not change, but let's use hybrid pi model. I'm going to put source here, GM-VGS. This is VGS. Then R0. Here we have drain and source. What's going to happen to source? Let's take a look at the actual circuit. At the source, this capacitor is shorted, is grounded, and this current source is open circuited because it is DC. So source is directly grounded. At drain, I have RD. The other end of the RD should be grounded because this source is killed. And then this capacitance is shorted. RL will appear directly in parallel with RD. So the equivalent circuit will be this one. There is RD and there is RL. And this will be my V out. So this is my small signal model for the common source amplifier. And as you remember, to be able to come to this point, I did DC analysis, verify that the transistor is in saturation, and then find GM and R0. GM and R0 we know right now from the previous stages. and my goal is to analyze this circuit. Analyzing means that I am looking for three important parameters. One of them is gain, of course, AV, V out divided by Vs. The other thing is Rin, the input resistance of this amplifier. And the last one is R out. These three parameters are important. Imagine that you're a designer, you design the circuit, fabricate them, and try to sell them to the customer. The customer wonders about your gain, how much gain you can provide. So AV is important. The customer wonders about what is the input resistance of this amplifier, because he or she is going to use it with a source that they choose. Similarly, they want to know about the output resistance of your amplifier because they wonder whether your circuit can drive their load or not. With that respect, input resistance is defined as the resistance seen from here. Okay, RS is excluded. So while finding input resistance, do not include RS. RS is out of your control. Source is out of your control. Why? Because the customer or the end user can use any kind of source. So you may not know the RS value. Similarly, for finding a route, it is the resistance seen from here. So you have to exclude RL. Do not include RL in output resistance calculation. So when you take a look at in this structure, Rin is the resistance seen from here, and it's obvious that it's going to be R1 in parallel with R2. But more officially, how would you find it? Of course, you are going to put a test source in here, Vx. Try to find Ix passing through it, and then find Vx over Ix to calculate the input resistance. But in this circuit, it's obvious that it's going to be R1 in parallel with R2, so you can write it directly. Rin is equal to R1 in parallel with R2. For the gain, how can you find it? We can do some tricks in here. First of all, as you may see, this R0, 1 and R0 is grounded because it's connected to ground. So R0, RD, RL are all in parallel. So you can write V out as the current passing through in this branch multiplied by the total resistance in here. And you have to be careful about the direction of the current. It's going in the reverse direction, so it's going to result in negative voltage. So I can write V out as minus Gm VGS R0 RD RL in parallel divided by V signal or Vs, whatever you call. So this is equal to V signal. I'm going to erase this right now because we may not need it anymore. And now I need to find VGS in terms of V signal. So VGS is this voltage. And in fact, VGS is VG minus Vs, which is Vg, because this is grounded. It is 0. So Vg is the potential in here. And you can use resistive voltage division in this loop. And you can write Vg in terms of V signal or Vs directly. And this will be equal to R1 in parallel with R2 divided by R1 in parallel with R2 plus Rs times Vs. So when you put this expression back in here, Vs's will simplify, and we will end up with this final expression. AV is equal to minus R1 in parallel with R2 divided by R1 in parallel with R2 plus Rs times Gm R0, RD, and RL. So this is the gain expression for common source amplifier. And there are some interesting results in here. First of all, we have a negative sign. What does this mean? Why do we have a negative sign? Because this current is going in reverse direction. So when you are finding the output resistance, the current is going in reverse direction. It's going to end up with like negative sign. And that negative sign penetrated till the end. So eventually you have a negative sign. So what does this mean? This means that input and output are in 180-degree phase shift. So this negative sign tells me that input and output have 180-degree phase shift. So if you apply some input signal with this phase, so we have signal like this. At the output, you will have the opposite one. So it introduces some phase shift. The other thing is that the first part, this part is in fact Rin divided by Rin plus Rs. So this is Rin. So you can write this thing as Rin divided by Rin plus Rs. And to be able to maximize the voltage gain, you want to maximize the input resistance, right? If you make Rin much larger than Rs, then this term will be quite close to 1, and you will maximize your voltage gain. And this is quite consistent with voltage amplifiers that we have discussed in the previous lecture. For the voltage amplifier, you always want large input resistance. So this mathematical expression exactly tells that. So for a good common source amplifier, you want Rin or R1 in parallel with R2 as large as possible. So you have to choose this R1 and R2 in the range of, let's say, maybe mega ohms, so that you maximize your voltage gain. Another thing in here, this R0 is the output resistance of the transistor. These two components are discrete components. You may not know it right now, but eventually you will learn it, and you can say it by intuition that discrete components have a resistance of in the range of like 1 to, let's say, 10K. But output resistances are in the range of 100 or 200 kilo ohms. So they are generally tend to be much larger than these discrete components. So this expression can be simplified as minus Gm Rd in parallel with RL if you are a good designer, if you choose input resistance very large, and if your transistor output resistance is much larger than the RD and RL values. So when you take a look at this expression, Gm is 2K NID, so you have to apply larger bias to have more gain. If you increase the DC bias current, it's going to increase Gm, and therefore you are going to achieve larger gain. Or you have to choose large RD value as much as you can to have large gain. You cannot play with RL, unfortunately, because as I said before, RL is set by the end user. You don't have any control on the load resistance. So let's stop in here, and in the next lecture, let's discuss more on this thing, and let's find the output resistance of this common source amplifier.